Thank you very much for your kind welcome. I would like to thank the University of Kiev and the Academy of Science of Ukraine for inviting me here and for giving me this opportunity to describe my own research in France. I called this talk today Juggling with Atoms and Photons in a Box. And I would like to describe experiments in which we have manipulated single particle of matter, isolated atoms, and single particles of light, which are called photons, which interact with each other. This is a kind of scientific research which has been recognized by the Nobel Prize in Physics in 2012. So I will not enter into the details of this research, but I'll try to give you the flavor of the experiments we have been doing. And I would like to give at the end an overview of related works which have been carried out in other laboratories which belong to the field which is called quantum information science, because by manipulating single particles, one has the hope to be able to develop new devices which will use the laws of quantum physics, the strange laws of quantum physics, to compute, to communicate, or to make measurements which are more precise, more powerful than what you can get with classical devices. But this will just be in conclusion of the talk. What we have been trying to do is to study single photons, single particles of light. And the first thing we have to do that is to trap the photons, because as you know, photons are flying away very fast at the velocity of light, and if you want to study them in the laboratory, you have to build up a simple device which keeps the photon inside the experimental apparatus. So what we do for that is to have a cavity made of two mirrors facing each other, and the photons are going from one mirror to the other one. They bounce back and forth between the mirrors, and they can stay in this cavity for a long time. We can trap a single photon or a field made of a few photons. But of course, the next thing we have to do is to be able to detect this photon and to manipulate the photon field. And for that, we have the photons interacting with single atoms which are crossing this cavity one at a time. And what we are trying to do is to observe the interaction of a single photon of light, of a single particle of light with a single atom, which is the most fundamental process of light-matter interaction. We have the simplest, we have a stage in which we have the simplest form of matter, a single atom interacting with a single form of light, a single photon, a single particle of light. By doing that, we test fundamental quantum laws, because at the level of single particles, nature obeys to quantum physics, whose laws are quite different from the one we are used to in classical physics. So we test fundamental quantum laws, and also we demonstrate elementary steps which one day could lead to quantum information devices. So to do that, we need first, of course, to have a special kind of atom which is very sensitive to light and which will be sensitive to the interaction with a single particle, with a single photon. So we use for that very excited atoms, which are called Rydberg atoms, from the name of the Swedish, the name comes from the Swedish spectroscopist in the 19th century, Johannes Rydberg, who was the first one to describe in quantitative terms the spectrum of atoms when they are in very excited state. These atoms are obtained by laser excitation. We start from an atom in its ground state, and by laser excitation, we promote a single electron of this atom to a very large orbit. So the atom extends over distances which are hundreds or thousand times bigger than the ground state of the atom. And because this electron is very far from the core, from the ionic core, it is very sensitive to all kinds of perturbations. So we use this system as a probe for the electromagnetic field in the cavity. This system looks very much like hydrogen, a single electron orbiting around a positive charge, which is a charge of the ionic core of the atom. It has a very big size and a very long lifetime. This electron can stay on this orbit for times extending to a fraction of a second. So it's a very sensitive and very long-lived probe. and it is especially sensitive to external fields, electric and magnetic fields, and also to microwave radiation. It's a kind of big antenna which can absorb and emit microwaves. And so the photons that we will be studying are microwave photons, photons which have a wavelength of a few millimeters, that is about 1,000 times longer than the wavelength of optical photons. And so what we are studying is how the atom will interact with a single microwave photon, which is resonant or nearly resonant with a transition between two Rydberg states. For example, if a photon is emitted, the electron will jump from one Rydberg state to another Rydberg state, and we are looking at this transition going from one Rydberg state to the next one by emitting or absorbing one microwave photon. How do we detect the atoms? How do we know that the atoms has gone from one electron orbit to the next one? I tried to explain it on this slide. In fact, what you see on this slide is the Coulomb potential of the atomic core, and the two states are very close to the ionization limit. There are two highly lying states in this Coulomb potential. One is a little bit less bound to the other. The orbit in red is a little bit less bound than the orbit in blue. How do you detect the atom? You apply a small electric field to this atom, static electric field, which add to the Coulomb potential a linear potential. And you see that what happens is that the energy barrier, the Coulombic barrier, is a little bit lowered by the fact that you have this electric field. And you see that you can extract the electron in the upper state while the electron in the lower state is still bound. So you have a selective way of detecting the atom in one state or in the other. What we can do next is to apply a ramp of electric field, an electric field which rises in time linearly, and you see that you will reach the ionization level for the upper state in a field which is a little bit smaller than the field required to ionize the upper state. And so the electron which is ejected from the atom will appear at slightly two different times, and this is the way we selectively detect the atom in one state or in the other. And you see that you get 1 bit of information per atom. Once the atom has interacted with the field, you ask the question, is the atom in the upper state E or in the lower state G? And we get 1 bit of information. The atom is either in one state or in the other. And if you want to get more information, you will have to send other atoms. And this explains why you have to keep the field for a long time. Because if the atoms interact one by one, you extract the information progressively from the field in the cavity. So these are general, this is the general way we do the experiment. We have to prepare single atoms to excite them into Rydberg state, to let them interact with the field in the cavity, and then to get information from the atom. So what can we do with these giant Rydberg atoms? As I will show you, we can use their huge sensitivity in order to observe the interaction of single atoms with single photons. We can also use Rydberg atoms to detect single photons without destroying the photons. And this is a very important point. What I will try, I don't know if it's me or, no, it's not me. It could be me, but it's not me. Usually when you detect photons, and I will come back to this later on, you destroy the photons when you detect them. What we do in our experiment is quite different. We let the atom interact with the photons in such a way that the photons are not destroyed. We get information about the field, but the photons are still there. And the last kind of experiments I would like to talk about is experiments in which we use the atoms to manipulate the quantum field in the cavity and to prepare the field into strange states which have counterintuitive properties. And this will be the last part of this description of our experiments about what we call Schrodinger cat states of the quantum field. So all these experiments belong to a field which has been called cavity quantum electrodynamics, cavity QED. We have Rydberg atoms interacting with photons in a very high Q cavity, a cavity which has a very high lifetime for the photon. before getting into these experiments, I would like to recall a few properties about the photon, which is a very ubiquitous and elusive particle. By ubiquitous, I mean that you have the photon is the most common particle in the universe. We have photons everywhere, and this room is full of visible photons, otherwise you would not see me, but also of microwave photons, of UV photons, and so on. And you have photons everywhere in the universe. It's also very elusive because the photon is destroyed very easily as soon as you try to detect it. I recall you that it has no mass, that it flies at the maximum possible velocity, which is the velocity of light, the speed of light. So if you want to observe it, you have to find ways to keep it at a given place. I also want to say that it carries almost all information that we have about the universe, all the information you have about the stars, about the galaxies, about the origin of the cosmic origin of the universe comes from the detection of visible UV and, most importantly, microwave photons of the cosmic background. And I show you here one famous picture of the cosmic background radiation. This is in false colors, and the different colors indicate the very slight variation, fluctuation in intensity of the cosmic background radiation coming from different parts of the universe. So this information is essential for all information we have about the world around us, the world on Earth, but also the world outside Earth and in the universe. And what is also very important to notice that the photon is usually destroyed while it delivers its message. All the photons which have been used to build the image that I show you here have been absorbed in the bolometers, in the detectors which have detected this radiation. In fact, in free space, the photon is eternal. The photons that you see on this picture have traveled 14 billion years through the universe without being destroyed, but they are destroyed as soon as they are detected. And you can say that the photons are very fragile and they do not survive long in captivity. By captivity, I mean putting photons, for example, in optical fiber. In optical fibers, photons can propagate over kilometers, which means microseconds, but not much more. And in the best possible cavities, optical cavities, the photons survive also a few microseconds. In our experiments, we were able to keep photons alive for about 1/10 of a second, which is a perceptible time, and have the photons interact with a very large number of atoms without being destroyed. So these experiments constitute what we call a new way to look, because detecting photon is the act of looking, but usually when you look, you destroy, and here we want to look without destroying. Why are we doing these experiments? I think I have also to remind you that photons are intrinsically quantum particles. In fact, the first time the photons was really mentioned in science is in the famous paper of Einstein in 1905, when he described the photoelectric effect and explained that in order to understand the photoelectric effect and to understand also the spectrum of the blackbody radiation, you have to admit that the electromagnetic field, which since Maxwell was supposed to be a wave, was also made of discrete particles, which later on were called photons. Each photon carries an energy E equal h nu, proportional to the frequency of the field, h being Planck's constant. And in a running wave, each photon carries a momentum, which is h nu over c, where c is the velocity of light. And this exchange of momentum between light and matter is at the origin of the radiation pressure effect. The photon is intrinsically quantum, and an experiment which illustrates the quantumness of the photon is the famous Young double slit experiment. You send light through a screen which has two slits, and on a second screen you see interference fringes. This experiment has been made by Young and by Fresnel in the beginning of the 19th century, and it was a proof that light was a wave. But at the same time, we can now do the same experiment with sources which are so faint, so weak, that only one photon at a time is emitted by the source. You can make single photon sources, and you can make this Young double slit experiment with single photons at a time. And you see on the right part of the slide how the interference fringe is built when the photons arrive one by one. At the beginning, you see discrete spots. And when the spots are discrete, you have the feeling that the photon is telling us, I am a particle. Look at the discrete spots when I arrive on the screen. And when enough photons have arrived, you see that, in fact, you have an interference pattern. And so collectively, the photons tell us, we are a wave. Look at the interference fringes. And this duality between the particle and the wave aspect is at the heart of quantum physics. It is true for photons, but it is also true for electrons, for atoms, and for all quantum particles. This is illustrated by this ambigram here. This sentence can be read either as light is a wave or as light is a particle. This ambigram was designed by Douglas Hofstadter, and you can find it on the internet. I think it's a way to show quantum ambiguity. Depending upon your state of mind, psychologically you will read either one or the other. In quantum physics, it is not your state of mind which matters. What matters is the way you do the experiment. It is the experimental apparatus which emphasizes either the wave or the particle aspect. So the study of the atom and photon interaction is called quantum electrodynamics. And if the photons are confined in a box, then it becomes cavity quantum electrodynamics. And this is a field that our experiment and other people experiment pioneered back in the 1980s. And it took many, many years before we were able to develop this experiment to the level which I will describe now. I also want to remind you that usual detection of light, precisely by the photoelectric effect I was mentioning before, is destroying the photon. What happens is that when a photon impinges on one atom, it extracts an electron from the atom if it has enough energy, if the frequency is high enough, and this electron is going away, and this electron is captured by a device, either by hot wire or by photocathode, and you get an electric signal. And this electric signal signals the presence of an electron, but the electron, of a photon, excuse me, but the photon has been destroyed in the process. And this happens also in ordinary vision. When you look at something, the photons which enter into your eye are transformed on your retina into a nervous signal going to your brain, but the photon is dead. And so the question we ask ourselves is, can one detect photons differently without destroying them? In fact, nothing in quantum physics prevents you from doing that. It's just a practicality that photons have been always destroyed by measurement. In fact, at the beginning of quantum physics, back in the 1920s, the founding fathers of quantum physics, you see here a picture of Einstein and Bohr discussing quantum physics in a Solvay meeting in 1927. They discussed the nature of the photon, and Einstein thought about an experiment in which photons would be trapped in a box, and the idea was to count the number of photons you have in the box, and at some point in time to open the box. So you see there is a shutter, and the shutter is controlled by a clock. So to let some photons escape at a given time, and to be able to measure at the same time the change in energy, that is a change in the photon number in the box, and the time at which the photon escaped. Einstein was hoping that in this way one could try to beat the Heisenberg uncertainty relation between time and energy. And the way he wanted to detect the photons was just to weigh the box in the gravitational field of the Earth. The photon energy means mass, according to E equal mc squared. And so if you have a given number of photons in the box, it will weigh a little bit more or a little bit less, depending on the photon number. So if you could weigh the box before and after the photons have escaped, you could find out how many photons have escaped. So I don't want to discuss the details, but this is a drawing by Bohr himself. Bohr tried to draw the experiment, and then he found why this could not be used to beat the Heisenberg uncertainty relations. But I don't want to enter into the details. I just wanted to mention this to show you that they have been thinking already about ways to count photons without absorbing them, without destroying the photon by the process. But of course, to weigh a box with photons inside is something which is completely unrealistic, and we will do it in a different way. In fact, in our experiment, what we have is the following design. We have two mirrors facing each other, and atoms are crossing the box one by one. These mirrors are, so we have one atom interact with one or a few photons in the box. I just want to give a few specifications about this box. It is made of copper, and the copper is machined in a very precise way, so you don't have any irregularity in the mirrors. So you cannot, photons cannot be scattered out of this cavity. And on top of that, we have coated a thin layer of superconducting niobium, which means that the photons cannot be absorbed. Niobium has zero resistivity, and so the photons cannot be absorbed in the mirrors. And so in this way, we have exceedingly good mirrors. In fact, the photons can bounce more than 1 billion times between these mirrors before being absorbed, which means that the photon can travel, if you unfold the trajectory, can travel 40,000 kilometers as compared to the few kilometers in an optical fiber, and survive for 1/10 of a second, or more than 1/10 of a second in this box. And the most difficult part of our experiment was to be able to design and to build a cavity which had this kind of quality. In fact, if you look, another way to look at it is to consider a very simple design. There are many elevators which have two mirrors facing each other. And when you enter into one of these elevators, you see your images being reflected back and forth. And when you look to the right or to the left, you see maybe 20 or 30 reflections of yourself. This is because the mirrors are not very good. If the mirrors had the quality of the mirrors I'm talking to you about here, you would see 1 billion times your own reflection. That is the population of China or the population of India corresponding to a single individual inside the elevator. So it tells you the kind of cavities that we were able to design. And so what you see is that a sequence of atoms crosses the cavity, couples to its field, and carries away the information about the trapped light. So you see that the atoms are going one by one through the system. What I want also to show you here is a connection with the thought experiment by Einstein and Bohr. So let's look at this box and let's try to compare it to the simple drawing that Bohr had made back in the 1920s. And for some reason, okay, you can see it now. You see the box, so you see on the left the thought experiment, on the right the real experiment, and you see the connection. Of course, the photon box is made by the mirrors, but you have also the clock. In fact, as I will show you in a moment, the Rydberg atom, which is crossing this cavity, acts as an atomic clock, and the information we get from the field is of the same nature as the information which an atomic clock is giving us about the measurement of time. So we can do either resonant experiments in which atoms emit and absorb photons in the box, or we can perform non-resonant experiments which prevent photons to be absorbed or emitted. For that, what we have to do is to slightly detune the cavity from the atomic transition. If we slightly change the distance between the mirrors, or if we apply a small electric field which slightly detunes the energy levels of the atom from the resonant condition, then the photons cannot be absorbed or emitted because this will violate energy conservation, but you still have a perturbation. It's called the light shift effect, and this is this light shift which will provide the information, non-destructive information about the field. So let's look first at the resonant regime. I show you here the principle of the experiment. You have a cavity which is initially empty, and you send one atom in the upper state of the transition. So the state of the system is E for the atom, 0 photon for the field. Then, at a later time, the atoms goes from state E to state G, and one photon is emitted in the cavity. So the notation is quite simple. Of course, in free space, this photon would escape, and this would be the end of the story. But in the cavity, what happens next, since the photon stays there, at a later time, the photon is absorbed again, and the atoms come back to the excited state, so we are back in state E0. And the fundamental quantum process is an oscillation between the state E0 and G1. It is called the Rabi Oscillation. From the name of the name, it comes from Isidore Rabi, who discovered magnetic resonance back in the 1930s, and this process is essential in magnetic resonance, the way atoms and photons exchange energy in a quantum way. In fact, this is also a process of reversible spontaneous emission. You see that the fact that the atom emits a photon is called spontaneous emission, but in the cavity, this process is reversible. At a later time, the photon can be absorbed, and you have an oscillation between the two states. And quantum mechanically, the system is described by a superposition of state E0 and G1. If you are at an intermediate stage between E0 and G1, the atom is simultaneously in E and G, and the field is simultaneously in 0 and 1. This is called the superposition principle of quantum physics, and this kind of experiment illustrates this principle. What you can do is to arrange the system so that when the atom exits the cavity, it is midway between E0 and G1. And so in this case, you have what is called an entanglement between the atom and the cavity field. The atom is at the same time E with 0 photon, and at the same time in G with 1 photon in the superposition of the two. It means that if you detect the atom at the end and find it in level E, you know that there is 0 photon in the cavity. And if you find the atom in state G, you know that there is 1 photon. And in a single experiment, you have equal probabilities to find one result or the other, but these probabilities are correlated for the atom and the field. This is called entanglement, and many experiments have demonstrated this, either with atoms and photons, or with pairs of atoms, or with pairs of photons. And this is one of the most fundamental processes in quantum physics, and I will come back to it at the end of the talk. So to do this experiment, what we do is that we send atoms one by one, and we let them interact longer and longer times, and we do the experiment again and again to develop statistics. And you see statistically how the probability to have the atom in level E evolves as a function of time. You see clearly the Rabi oscillation on this curve, and you see that if you stop the evolution midway, you prepare this entangled state, and if you stop this oscillation after 1/2 period, you are exactly in the state G1. So this provides also ways to prepare photons on demand. You just let the atom and the field interact for a well-defined time. So these are demonstrations of simple quantum operations. And the question that we can ask yourself now is, how can you detect the photon? Okay, you can prepare 1 photon, how can you detect it without destroying it? For that, I need to discuss another ingredient in the experiment. We prepare Rydberg atoms, not only in very excited state, but we prepare a special kind of Rydberg atom, which is called a circular Rydberg atom. By circular, I mean that when the electron is excited, it ends up in a circular orbit around the atomic core. So for that, you have to have the atom absorb laser light to be excited, and also absorb circularly polarized radio wave photons in order to increase the angular momentum of the electrons until you get a circular state. And this process has been invented by Daniel Kleppner at MIT, who has been the first to do experiments with circular Rydberg atoms. So I show you here, on this slide, you see the orbit of a circular Rydberg atom. And I just use the minimum quantum physics required to understand what's going on. In fact, quantum physics means that the electron is a wave also. And you see that this electron wave is circling around the nucleus. And the quantization condition is that you need to have an integer number of wavelengths. It is called the de Broglie wavelengths you need an integer number of de Broglie wavelengths around the core to make the orbit stable. And so the excited state E, which has the principal quantum number 51, means that you have 51 wavelengths around the circular orbit. And of course, in this circular orbit, the electron is completely delocalized. You have the same probability to find the electron anywhere on the circle, which means that this system has no electric dipole. The center of the positive charge and the center of the negative charge of the electron coincide, so there is no electric dipole. If you want to prepare an electric dipole, what you can do, and what we do, is to prepare a superposition of the n equal 51 state which I'll call E, and of the n equal 50 state which I'll call G. And you see immediately what happens. In fact, you have two waves which are superposed. One wave has just one node more than the other, which means that at one end of the orbit, the two matter waves add up, interfere positively, and at the other side of the orbit, the two waves subtract from each other, they interfere negatively. And you see now that you have an orbit, the superposition has an orbit which has a kind of banana shape, a crescent shape, and now the electron has a center of gravity which is different from the nucleus, and you have an electric dipole. And this electric dipole is rotating at 50 gigahertz around the core. And to do that, what we need to do is to apply a pulse of classical microwave which superposes the states E and G. And so applying classical microwave pulses before and after the atom interact with the cavity are essential ingredients in this experiment. What can you say about this localized wave packet? It revolves around the nucleus, and it looks like the hand of a clock. If you can count the rotation at 51 gigahertz, you have an atomic clock. And in fact, the atomic clocks work along this principle. I also showed on this slide the picture of Niels Bohr, because this model, this simple atom in which the electron is rotating like a planet around the core, is the original Bohr model for the atom. And the condition that you have an integer number of de Broglie wavelengths is the equivalent to the initial quantization condition that Bohr introduced in 1913 to explain that matter was quantized. So it was the next step of Einstein in 1905, which showed that the light was quantized. It was the 1913 paper by Bohr, which showed that matter was also quantized. Then came de Broglie in 1923, and then the full-fledged quantum theory by Schrodinger and Heisenberg in 1925-26. What I want to emphasize here is that our Rydberg atom is a very simple object. It's almost classical, just an electron around the core. The only bit of quantum physics we need to understand it is to add this de Broglie wavelength condition. And you could use classical models to describe everything about this atom. And what is very remarkable is that although the system is almost classical, it will display very strange and very strong quantum features, as I will show you in a moment. So how can you now use this atom to detect photons without destroying them? For that, you have to go to a non-resonant interaction. You have to slightly detune the atom from the cavity field, because we don't want the atom to be able to absorb or emit photons. But then what happens is that when an atom interacts with non-resonant light, the energy levels of the atom are slightly modified. This is called the light shift effect. And this light shift effect was discovered in 1961 by Claude Cohen-Tanucci, who was my thesis advisor 50 years ago at École Normale Supérieure, and I will say a few words about him at the end of the talk. But these light shifts are very important in modern atomic physics. It means that if an atom enters into a light field, it will experience a shift of its energy level, and the gradient of this energy shift, the fact that the light field is spatially variable, means that the atom experiences a force, and this force is able to trap cold atoms. And so the light shifts are essential for all the physics of cold atom trapping and manipulations, which have developed into a huge field of atomic and quantum optics physics. And this is one aspect of this that I would like to describe here. you see that what will happen is that when the atom will enter in the cavity, if it is in level E, its energy levels will be slightly shifted upwards, and if it is in level G, its energy levels will be slightly shifted downwards, which means that during the short time the atom is in the cavity, its electric dipole will evolve at a slightly different frequency, which means that it will accumulate a phase shift. So the dipole will not emerge from the cavity along the same direction as it would if there was no photon inside the cavity. And this effect is, of course, proportional to the number of photons, that is, to the intensity of the field. And so you see that basically this effect produces a phase shift of the atomic dipole, and if you are able to measure this phase shift, you will count the number of photons. And in fact, the Rydberg atoms are so sensitive that this phase shift can reach the value pi, which means that a single photon can make a huge difference. The dipole will emerge in one direction if there is 0 photon, and in the opposite direction if there is 1 photon, which I have tried to show you on this, drawing. You see that if there is 0 photon in the cavity, the dipole emerges in one direction, and if there is 1 photon, it emerges in the opposite direction. And if you are able to measure this phase shift, then you will measure the photon number without destroying the photons. So it's a non-destructive detection. So how do you do that? In fact, we use exactly the same setup which is used in an atomic clock. And it's just an atomic clock which is delayed by the photons which are trapped inside the clock. So you see the design of an atomic clock is very simple. On the left, you have the box where the photons are prepared into the circular state. They drift across the cavity, and in the end, they are detected by field ionization. So you get 1 bit of information per atom. In the middle, they cross the cavity, which contains the field that you want to measure. And there is very important addition to that. You have here 2 classical cavities, R1 and R2. The first cavity is used to prepare a superposition of state E and G. That is to prepare an electric dipole. This dipole starts rotating, and the pulse applied in the second zone, R2, at a later time, will catch the electric dipole in one direction. And this combination of these 2 pulses realizes what is called a Ramsey interferometer, which is the basic design of all cesium atomic clocks, which are the standard of measurement of time. What Norman Ramsey, who invented this design, showed is that when you tune the frequency of the radio field in R1 and R2, you get interference fringes, which are quite similar to the Young double slit experiment, because you subject the atom to 2 pulses, and there is a quantum interference effect between the action of these 2 pulses. And in atomic clocks, what you have to do is just to lock the system at the tip of the central fringe, and then you have locked your microwave to the atomic transition, and this gives you the atomic clock. In our case, what we do is that we arrange the system in such a way that a single photon will shift these fringes by half a fringe. So it means that you will see the blue fringes. You will see the blue fringes if you have 0 photon in the cavity, and the red fringes if you have 1 photon. And if you sit on top of the red fringe, you see that the atom will emerge from the system in one state if there is 0 photon, and in the other state if there is 1 photon. So you have just to tune in the proper way your system and to get a pi phase shift per photon for your system. This was the original proposal we made with Michel Brune, Jean-Michel Raymond, and other colleagues back in 1990 to detect photons without destroying them. And it took us 16 years between the proposal until we were able to perform the experiment. And this gives you an idea of the time scale of this kind of basic science experiment. On this slide, you see the result of the experiment. You see the fringes that we obtain if there is 0 photon in the cavity in blue, and if there is 1 photon in the cavity in red. In fact, what we measure here is just the parity of the photon number, because of course if you have 0, 2, and 4 photons, you will get the same fringes. If you have 1, 3, and 5 photons, you will get the same fringes. But if the photon number is very small, if you are sure that you cannot have more than one photon in the cavity, what you get is a system which tells you whether you have 0 or 1 photon. And you see here at the bottom a trace lasting 2 seconds showing how the field in the cavity evolves as a function of time. If you find the atom in the blue level, E, it means that you have 0 photon in the cavity. And then suddenly the signal shifts to the red line, meaning that the atoms are detected in G, and then you know that you have 1 photon. And the way the system just clicks from 0 to 1 is just a natural way. Your cavity is very cold, and according to Planck's law, radiation law, you have a high probability to have 0 photon in the cavity, and a small probability from time to time that the thermal fluctuation brings 1 photon inside. And you see that this telegraphic signal really tells you first that the field is quantized, that you have quantum jumps. You see that the field changes suddenly from 0 to 1 at random time and from 1 to 0. And also that the method is non-destructive, because you see that many, many atoms will agree with the fact there is 1 photon, whereas with usual photodetection, the first atom which detects a photon will kill it. So it's a non-destructive way. And also, I want to say that this experiment can be understood as a quantum logical gate. The photon, which can take state, the field, which can be in state 0 or 1, interact with the atom, which can be E or G. Each of these two subsystems is a quantum bit, because it carries only 1 bit of information, and 1 bit controls the state of the other in a quantum way. And this is an example of what is called a quantum logical gate in quantum information theory. So we can also, now I can describe to you a more recent experiment. You can also use the light shifts in order to project the photon number in the cavity into a given number value. For instance, when you prepare classically the field in the cavity, what you do is that you send a pulse of microwave, which has a well-defined phase inside the cavity. If the field has a well-defined phase, it cannot have a well-defined photon number. It means that what you prepare is a field in a superposition of different photon numbers. This is a consequence of Heisenberg uncertainty relation. A classical field has a well-defined phase, so it cannot have a well-defined photon number because there is an uncertainty between the photon number and the phase definition. So what you prepare, in fact, is a field which can have 0, 1, 2, 3, 4 photons, according to quantum physics. But the question we can ask ourselves, can we, by letting the atom interact with the field interact with a single atom, can we force the field to decide how many photons it has in it? In other words, can you answer the question, does the cavity contain a given number, n0 photons or not? And this amounts, according in the language of quantum physics, to measuring the projector on the state n0, the state which has a well-defined photon number. And it's also, in the language of quantum physics, it corresponds to measuring an observable which has the eigenvalue 1 if there is n0 photon, and the eigenvalue 0 otherwise. So you answer by a yes or no answer to a simple question. And you can do that with a single atom. What we have to do is to perform high-resolution spectroscopy of the atom cavity system, which is able to resolve in a single shot the single photon light shift. So for that, and you see here the picture, we need to work with a system with 3 levels. So 51 and 50 C are the circular states corresponding to principal quantum number 51 and 50. And we have to consider also the circular state with the principal quantum number 52, which is just above. And we tune the cavity a little bit out of resonance with the transition between 50 and 51, which means that we have light shifts on this transition. So the cavity photons shift the level 51, but they don't shift the level 52, which is far off resonance with the cavity. So if you look at the transition between 52 and 51, you see that this transition is light shifted by an amount which is proportional to the photon number in the cavity in the cavity field. And so if you are able to resolve this spectrum, you will be able to find out how many photons you have in the cavity. So for that, you apply a microwave, which has a frequency corresponding to the transition corresponding to a given photon number. But of course, your microwave spectrum has to be narrower than the distance between two peaks. And this means that the interaction has to last long enough, because you see that the width of a microwave transition is inversely proportional to the time it takes to apply it. And so you see that if you want to achieve this, you require to have high resolution, which means slow atoms, atoms which cross the cavity in a long time. And for that, we modified our setup. You see now the atoms are cold atoms, and they are sent up, and they stay a long time in the cavity. It's a kind of atomic fountain in which the atoms turn around when they reach the highest altitude. And these slow atoms spend more time in the cavity, and we are able with this slow atom to perform much more precise measurement than the one we were doing before. So the circular states need to be prepared in the cavity, and they are prepared by circularly polarized radiofrequency photons, which are produced by electrodes which surround the cavity. So I don't want to enter into the details, but I just want to show you here that if you do that, you see that now if you tune your microwave, you will see distinctly the peaks which correspond to the different photon numbers. And this is a picture which shows also very clearly that the field is quantized. Each peak corresponds to a different photon number. And you see also that if you tune your microwave at the top of one of these peaks, as soon as you will detect an atom in the corresponding level, you will know that you have this photon number. And we were able to perform this experiment recently. I show you here, I will show you here when it accepts to move the result. I think my computer is blocked. Okay, I think I have to start the computer again because in order to decide how many photons we have in the cavity, once you have filtered a given photon number, what we do is that we put the cavity in exact resonance with the field. And so you see here the way the experiment is done. First of all, we prepare a given photon number, then we tune the cavity in exact resonance, and we observe the Rabi oscillation. And the frequency of the Rabi oscillation depends upon the photon number. So you see here that we can distinguish Rabi oscillation corresponding to 0 photon in the cavity at the bottom, 1 photon, 2 photons, 3 photons, 4 photons. The Rabi oscillation goes faster and faster because the field is bigger and bigger. And from this Rabi oscillation, we can know exactly that we have prepared a given photon number. So I'm sorry it took a lot of time to get to this point. But I would like now to finish with the Schrodinger Cat problem. Up to now, I have described to you experiments in which the light can be considered as an ensemble of photons. So you count photons, and this emphasizes the particle aspect of light. So can we do experiments which will instead emphasize the wave aspect of light? And for that, we have to do an experiment which measures the phase of the field and not the photon number, because phase and photon numbers are complementary variables. And this experiment, which I will show you now, illustrates the complementarity principle and the Schrodinger Cat paradox. So what we do, well, I remind you first what is the Schrodinger Cat paradox. You know about the story of Schrodinger. Imagine that a big system like a cat is put in a box with a single atom. And if the atom is excited, nothing happens to the cat. If the atom falls in the lower state, it emits a particle which triggers a device which kills the cat. So what will happen if the atom is in a superposition of being excited and not excited in the same way as I discussed in the previous experiments? Then, according to Schrodinger, the cat should be in a superposition of being dead and alive. So this is the essence of the paradox. The superposition principle leads you in an inescapable way to the fact that system could be in different states at once. But of course, and it leads also to the notion of entanglement, because here the atom and the cat are entangled. But of course, this also is absurd at the macroscopic scale, and Schrodinger said one never saw a cat which is dead and alive. So when you go from the micro world to the macroscopic world, there is something which prevents you from seeing this superposition. And this is called the problem of decoherence, or the problem of the boundary between the quantum and the classical worlds. So we did an experiment which illustrates this at a micro scale. We start by preparing a coherent state of the field in the cavity, which is a state which has a well-defined phase. And I just remind you that the classical field, which is just an electromagnetic field which oscillates as a function of time, has an amplitude, a frequency, but also a phase. And you see here 3 fields which have the same amplitude and frequency, but different phases. They vary only by the time at which they reach their maximum. And we know that this phase information can be symbolically represented in a plane. This is called the Fresnel representation, or the complex number representation. A field is represented by a vector whose amplitude is proportional to, whose length is proportional to the amplitude of the field, and whose direction gives you the phase. For instance, here 3 fields which are 120 degrees out of phase with respect to each other are represented by 3 vectors which are like I have shown here. This is classical. In quantum physics, the picture is a little bit more complicated, and the coherent field is a vector whose tip is fuzzy, because you cannot define with exact precision the amplitude and the phase at the same time. This is Heisenberg uncertainty relation. So the field is represented by a vector whose tip has a Gaussian distribution in phase space. So, and this Gaussian distribution is shown here in coded colors. Red represents maximum amplitude, and the green 0 probability amplitude. So what happens to such a coherent field when it interacts with a single atom in our cavity? I have tried to represent this here. You see that what happens is that you start by preparing a coherent field inside the cavity, just a classical microwave field. And then you send across the cavity a single atom. And before the atom enters in the cavity, you prepare it in a superposition of 2 states. So what will happen now is that the atom will shift the frequency of the field. This is a reciprocal effect of what I said before. The atom shifts the frequency, the field shifts the frequency of the atom, and conversely, the atom shifts the frequency of the field. This is a refractive index effect at a single atom level. And when the atom crosses the cavity, you see that the field will be shifted in one direction if the atom is in level E, and in the other direction if the atom is in level G. So when the atom emerges from the cavity, the field is prepared in the superposition of being in one direction and in the other. This is a Schrodinger cat situation. The atom has forced the field to assume 2 phases at once, exactly as in Schrodinger cat's experiment, where the atom forced the cat to be at the same time dead and alive. So what happens next, of course, if you detect at this time, you will find the atom in E forcing the field to take one phase, or you will find the atom in G forcing the field to take the other phase. The trick is to let the atom cross the second Ramsey zone, R2. And when the atom crosses the second zone, R2, what happens is that the levels are mixed again. And when you detect the atom, you do not longer know which was the state of the atom when it crossed the cavity. And then what quantum physics tells you is that when you detect the atom in E or in G, it projects the field into a cat state with a plus sign, dead plus alive if you detect the atom in one state, or dead minus alive if you detect the atom in the other state. So this is a very simple experiment in its principle. And what you can do next, once you have prepared this cat state, is to reconstruct its quantum wave function. I don't have time to explain you how we do it, especially because my computer made us lose a lot of time. But this is what you get. This is an experimental signal. You see the 2 Gaussian peaks represent the dead and alive cat. And in between, you have interference fringes, which is a signature of a quantum interference, which tells us that you are in a coherent superposition of one phase and the other. And so this is a direct view of this quantum superposition situation. And this is obtained for a field which contains a few photons. What we did next, and this was an experiment that we did about 10 years ago, and in which Igor Dodsenko, who helped me to fix the computer, helped us to do in Paris. It was already there at that time. What we do is just to look at the Schrodinger cat as a function of time, and you will see that the fringes disappear very rapidly if the experiment works. Let me see if this works. Where is the arrow? Okay, yes. If you look at the fringes, the movie shows that the fringes disappear quickly. After about 20 milliseconds, you have no fringes left. This is an experimental evidence of decoherence, the fact that you start with a cat which is at the same time dead and alive, and you end up with a cat which is dead or alive, and no longer any coherence between the two. And this disappearance of the fringes of the coherence signal is an evidence of the transition from quantum to classical. You can keep a quantum system for some time, but after some time, due to the fact that the system is coupled to its environment, the quantum coherence disappears. And this is a big problem if you want to build a quantum computer, for instance, and I will conclude with that in a moment. I want to conclude by recalling you what Schrodinger thought about all these thought experiments. This is a sentence which has been repeated many times. Schrodinger used to say, we never experiment with single electrons, atoms, or small molecules. In thought experiments, we assume that we do, and it always results in ridiculous consequences. So what we wanted to prove in our experiments is that the consequences are not ridiculous, that you can really do that. Of course, Schrodinger knew that single particles did exist. And in fact, when he wrote that in 1952, there was bubble chambers, there was a lot of detectors in high energy physics where single particles were detected. But what Schrodinger said is that it was a completely different story. He said it is fair to state that we are not experimenting with single particles any more that we can raise ichthyosaurus in the zoo. We are scrutinizing records of events long after they have occurred. So in high energy physics, what Schrodinger said is that you don't see the event as it occurs. You see the signs, the remains of a past event. And what he thought is that it would be forever impossible to observe a quantum system making quantum jumps and studying it in the way that I described. And of course, our experiments on photons proved Schrodinger wrong, as many other studies on quantum particles which have been performed during the last 30 years. So this field of research is blossoming now. The goal is to try to harness individual quantum systems, which can be atoms or photons or electron spins or artificial structures, in order to achieve tasks which with classical device, which would be impossible with classical device for computation, communication, or precise measurements. And this is a domain of quantum information science. And in the last couple of minutes, I would like just to review very rapidly other domains in quantum optics where this is being attempted. You see here, for instance, 5 beryllium ions in the lab of Dave Wineland. These are ions which are kept in the trap, which is with electrodes are seen at the top and the bottom. And you see that each atom appears as a small, shiny star. In fact, what one is doing is to illuminate the atom with lasers, and the atom scatters a lot of photons into a microscope, and you see them as individual points. And each of these atoms has 2 levels, and you can, according to the frequency of the laser, excite in one or the other. So each atom behaves as a qubit. You see here a more recent experiment where you see 14 calcium ions in the lab of Rainer Blatt in Innsbruck, and then 30 ions, calcium ions. Each atom is a 2-level quantum bit, which can evolve into a superposition of 0 and 1. And you see that if you have 30 of these atoms, the number of quantum states is 2 to the 30. 2 to the 30 is close to 1 billion. So you see that the chain of atoms has 1 billion quantum states, and you can prepare it in a superposition of these 1 billion states. So you have a huge space of state that you can manipulate. And this is a topic of quantum information science. It's a kind of atomic abacus for trying to perform this kind of quantum computation. You can do also 2-dimensional lattices of cold atoms. This is a two-dimensional lattice which is obtained by trapping atoms in potential wells made by having lasers interfering with each other. Each of these spots is a single atom that you can address and manipulate. Comes from the lab of Emmanuel Black in Garching. So what can you do with these things? What I want to just to stress is that each of these systems is a quantum simulator. It emulates what happens in real physics, but at a different scale. In condensed matter physics, the atoms are about a few angstroms apart. Here, the particles are a few microns apart, and they interact, of course, much more weakly because they are much further apart from each other, which means that the system is much more fragile and has to be maintained at a much lower temperature. But the physics is the same, and the laws of quantum physics are the same. So you can arrange atoms in artificial structures which simulate situations occurring in real materials at different scale. So one can control the atomic position and the way they interact with each other, and one can in this way test new physics. I like to make a comparison with a chess game. When you play chess, you put the different pieces at different positions, and the pieces interact with each other according to some kind of Hamiltonian. Depending upon the value of the piece, they interact in different ways. Here you can do the same. You can put atoms at different places, and you can tailor the way they interact with each other. You know that a classical chess game has a huge amount of possibilities, and only recently classical computers have been able to beat humans at chess game because the number of possibilities is finite, or at least can be measured by numbers. If you play the game in a quantum way, it means that each piece could go in a superposition of states, and then the number of possibilities becomes so huge that no classical computer could solve the problem. On the other hand, if you have the real system and you observe it, you have what is called a quantum simulator, and you can find new distributions of pieces, that is, new configurations which might have interesting properties. So this kind of system could be used to study, to try to find out the way to synthesize novel materials with interesting properties, for instance, to try to find superconductivity at room temperature. So in our lab, we are trying to do an experiment along this line with circular Rydberg atoms. And we have proposed, Michel Boyne, working in our lab, has proposed a project in which we would have a string of circular Rydberg atoms, which will be kept at well-defined position, having them interact with each other in a tailored way to try to find out new phases. This simulates a chain of spins interacting with each other, kind of chains that you can find in many condensed matter physics problems, but I don't want to enter into more details here. I mentioned something which is related to a question which was asked to me before. What about quantum cryptography? If you have two particles which are entangled with each other, the entanglement will survive after separation. For instance, you can have two photons. Each photon can take two polarization states, which are called 0 and 1. If they're entangled, if the first photon is found in state 0, the second will be found in state 0. The first in state 1, the second will be in state 1. But also, if you prepare a superposition, if you measure a superposition of 0 and 1, the second will be found in the same superposition. And this property will survive large separation. The photons could be sent across optical fibers, propagate along many kilometers, and you will have the same result at the two ends, which means that it is as if two distant dices were yielding the same result, because the result for each measurement is random, but you have the same randomness occurring at the two different points. And this kind of non-local randomness is something that Einstein didn't like at all. He thought that there was something missing in quantum physics which should be able to avoid this kind of situation. But all the experiments which have been done during the last 30 years have proved that, in fact, it is the way nature behaves. The randomness of quantum physics is indeed non-local. And this non-locality could be used for cryptography. You could use the fact that the same randomness occurs at 2 points to have a series, a sequence of random numbers shared between two partners. And if someone is trying to steal this key, he will not be able to do it because the key is produced during the measurement. There is nothing which propagates between the two partners. So this is a way to perform cryptography while being sure that nobody is watching. The technology is demonstrated, but the progress remains to be done in order to be able to share with enough speed, long keys, and so on. And this is a very active field in quantum communication. Quantum metrology is also a very active field. the fact that if you are able to prepare these very fragile superpositions, their features are much more fragile, much more sensitive to perturbation than classical system. For instance, here you have a Schrodinger cat. If you are able to make a measurement which is sensitive to the, which will shift the fringes of the Schrodinger cat, you will be able to make measurements of small electric or magnetic field with a much higher precision than in these classical devices, and we have been doing this kind of experiment in Paris. Novel clocks based on this non-classicality of quantum states of the atoms in the clock would be able to make clocks with even higher precision than now. Now clocks have reached a precision which is better than 1 second in the age of the universe. With quantum states of atomic system, entangled atoms in the clock, one should be able to make even better clocks with various possible applications. So you can build novel kinds of gyros, gravimeters, magnetometers, electrometers using these systems. And I end up with quantum computers because I am always asked questions about quantum computers. What I want to say is that the precision, the power of classical computers has increased over the last 50 years in a tremendous way. Each 18 months, the power and the memory have increased, have doubled. And this is mainly due, essentially due to the fact that the size of the transistor has been decreased. And this is Moore's law. If you decrease the size of the transistor, you can pack more and more transistors into a given volume, and you get more and more power and more and more computer power. But you see that this straight line comes to the size of a single atom for a transistor right now. We are reaching now, this year or next year, the point where if you extrapolate Moore's law, each transistor will have the size of a few atoms. And at this point, you cannot go anymore in this direction. You cannot make transistors smaller than 1 atom. On the other hand, if you can make use of state superposition, you will increase a whole new world of possibilities because you will be able to have computers which will be able not only to distinguish between 0 and 1, but to use all the superposition of 0 and 1 and all the capacities of entanglement. So this is the rationale, at least, for quantum computers. But of course, this is a very difficult problem. A quantum computer will be a huge Schrodinger cat, which will be able to compute on different states at once and using the properties of interference to get the right result in the end. The decoherence is, of course, a big enemy because decoherence destroys state superposition. And one way around that would be to be able to observe decoherence and to be able to correct for it. This is called quantum error correction. And it is, progress have been made, but we are still very far from being able to control that. We have also to find the suitable qubit candidates. Should it be ions in traps or superconducting circuits? There are many possible candidates. You have also to find useful algorithms, which is not so easy. There are only a very few algorithms which have been proven, among which the factorization algorithm. And much more experimental and theoretical work remains to be done. So I think I've been long enough. I will just conclude by a few remarks. I would just want to say that blue sky research, the kind of research that I've been describing, is unpredictable. It's impossible to say when and if a quantum computer will be actually possible. And this has been shown in the past by many examples. For instance, when the laser was invented back in the 1960s, nobody envisioned the wealth of applications they would lead to. Nobody was able to predict that lasers would be able to make atomic clocks so fantastically precise, or to be able to be used to detect gravitational waves, which happened 2 years ago. So lasers were there, but nobody knew exactly what to do with them. Highly transparent optical fibers were developed in the 1970s, and also the application was not clear. Computers made huge progresses since the discovery of the transistor. And when you put all this together, you reach the global communication network. And nobody would have dreamed about it 30 or 40 years ago. So the question is, will there be a quantum internet, possibility to entangle nodes at large distances? Maybe yes, maybe no. Nobody can say it, but the research in this direction is certainly very interesting. So I would like to conclude by thanking a few people. First of all, I show this picture. This picture was made 52 years ago in the lab of Alfred Kastner and Jean Brossel on the day the Nobel Prize of Alfred Kastler was announced. Kastler was the thesis advisor of Claude Cohen-Tanucci, who was my thesis advisor, and I was in the lab at that time. You see me here. I did not look like I look today. And Claude Cohen-Tanucci is near Kastler. Kastler had invented with Jean Brossel the method of optical pumping, which was the first way to use light to manipulate atoms. So this is certainly the ancestor of all the kind of experiments we are doing now in quantum optics. And you see on this picture that this school has been very successful since Claude Cohen-Tanucci got the Nobel Prize something like 31 year later, and I got my prize in 2012. And I want to say that this was the same for, I shared the Nobel Prize with David Wineland, who was working on ion traps, and Dave Wineland was a student of Norman Ramsey, which I mentioned, who also was a Nobel Prize, and Norman Ramsey was a student of Isidore Rabi, who was the inventor of magnetic resonance, and Isidore Rabi was a friend of Kastler. And I remember when I was in '66 in Paris, one day Kastler came with Rabi, and in the evening they went to the theater and they saw a play about, which was called the Oppenheimer case, which told about the story of how Oppenheimer was persecuted during the McCarthy era, and Rabi defended Oppenheimer at that time. So it's very important to have good masters, but it's also important to have very good students. And the picture that you see on the right was taken in 2012, exactly in the same room as the first picture, because it's the room in which I did my research with my co-workers, and I want to signal, to give the name of two of them, Jean-Michel Raymond and Michel Brune, who really did all these experiments with me over many, many years. And you can see on this picture also Igor Dotsenko, who is sitting here and who had joined our group in 2007. And this group has still, since then, moved to Collège de France. And you see here we have a much better lab, and we work in the center of Paris with a very good surrounding, as you can see on this picture. This picture was made at the top of the lab. And I will end here and really apologize for the failure of my computer. I think I have to change my computer. This is one conclusion about this talk. Thank you.
So thank you for your attention. So now we propose to ask questions to this presentation. And if you have general questions to anything else, it will be afterwards. So do you have questions to this talk? And again, either in English or Ukrainian.
Question over there.
What are the supposed sources of decoherence in the experiment of that movie you showed?
Okay.
Is it thermal cause decoherence or its direction?
No, in this experiment, it's not thermal. We are almost at 0 degree. What happens is that sometimes a photon escapes. And as soon as this photon escapes, it carries away some information about the phase of the field in the cavity, so it forces the field to choose one phase or the other. And in fact, the decoherence time becomes shorter and shorter when the photon number increases for a very simple reason. The probability that the first photon will escape will become bigger and bigger in a given time if you have more and more photons. It's clear that if you have 10 photons, the first photon will escape in a much shorter time than if you have only one photon. Because the cavity damping time is the average time for the escape, but if you have a large number of photons, the first photon will escape in a time much shorter than the average time. So, in fact, what we observe here is the leakage of information in the environment, which is technically due to the fact that the mirrors are not perfect. And it's very often the case. If you prepare many atoms in an entangled state, the first atom which will have a perturbation will destroy completely the entanglement between the atoms. The same, so it means that it becomes more and more difficult to protect the quantum system when it becomes larger and larger. Yes. Yes. Yeah, it occurs faster, and And this is a general idea about decoherence. If you take a cat, for instance, you will never be able to prepare the cat in a given quantum state before decoherence, because the cat has to interact with thermal photons, with its environment just to breathe. And this coupling to the environment makes it impossible to define the wave function of the cat to start with. So a cat is not a pure quantum system, and so decoherence occurs immediately. Yes?
Which sources were used in your experiments to obtain single photons?
Yeah.
Although there is told you some specific experiments which allow achieving single photon at a time, or just some ultra-short laser beams?
Good. Yeah, can you repeat? I didn't understand.
So which sources were used to obtain single
Okay.
photons in your experiment?
In our experiment, it's two possibilities. Either you send a single atom and manage for this atom to make just half a Rabi oscillation. So the atom lives in the lower state and deposits one photon. Another way is to prepare a field which has many photon numbers in it, and to filter out one photon number by using this nonlinear interaction with the atom. So we use both techniques. You can prepare single photons either with single atoms or by measuring, by making a quantum measurement on a field which contains many possible photon numbers. Depends what you want to do. I think the second method is more interesting in relation with quantum information, because the kind of interactions that you are looking at are the same which are used to demonstrate quantum gates and to demonstrate simple basic features. The first method allows you to prepare one photon, but you can also use, once you have one photon, to prepare a second one and then a third one. You just have to make the Rabi oscillation faster and faster as the number of photons increases. It has also been used in our device or in superconducting circuits. So it depends what you want to do, but both methods can be used. Yes?
My question relates to the experimental setup. Could you please explain, just in some words, how to prepare this hydrogen-like atom?
Okay.
And are there any restrictions as to the method? Or practically any element, any chemical element can be found?
Yeah. Of course, we choose rubidium because rubidium can be easily excited with laser diodes, which are very simple laser system. But other people we had been working with Rydberg states of sodium or cesium or all kind of alkali atom. It's easier to work with atoms which have one valence electron, because then the core is very simple. The core is like a rare gas. But you have also Rydberg states with two electron atoms, whose spectroscopy is more difficult. The way we prepare them is, of course, first of all, to excite the electron to a very large orbit, either with one laser pulse or stepwise. We go to a first excited set, then to a second one. And then you prepare, of course, in this way, you prepare a low angular momentum Rydberg state, because you put only 1 or 2 units of angular momentum, one for each photon. This corresponds to a very elliptical orbit, classically, which means that the electron can get very close to the core. And this means also that its lifetime is rather limited, because when the electron gets close to the core, its acceleration is big, and there is a huge Bremsstrahlung, and the lifetime is short. The circular Rydberg atom is an atom which has a very long lifetime, because the electron is always away from the core and has a small acceleration. But to prepare that, you need to feed a lot of angular momentum in the system. It's why you need circularly polarized radiofrequency photons. So we have the excitation is in 2 steps. First of all, we give the energy, and then we feed the angular momentum. And there are many ways to do it, which are variants of the method that Daniel Kleppner invented in 1982. We use a variant of this method, which is very effective, and which allows us to prepare these circular atoms with which you can do a lot of things which I did not describe here, different from the experiment that I described today. Okay.
So any other question? Don't be shy.
Yeah.
My question is following. Does it matter, does it make a difference in which location do you shoot the atoms through a cavity? Because in the cavities there is supposedly a standing wave.
Yes.
And it makes me think that in some places the electric field is zero,
Yeah.
which will, if you
Of course, if you send the atom at a node of the cavity field, it will not see anything. And so we do the opposite. We try to send the atom at an antinode where the field is maximum. And of course, you have to adjust all the experimental setup for that. But we made some tests in which just if you move your atomic beam along the standing wave, there are some points where it does not see anything, of course, and that's not the point where you want to stay, of course. Yes. Yes, of course, yes.
Other question?
Питань немає, тому подякуємо пану Сержу.